Hello everyone, and I welcome you all to lecture 4, where we are going to see the energy accounting. So energy balance, actually energy accounting for closed systems, energy accounting for closed systems. And if you recall from our lecture 1, where we have defined closed systems, so we know that in closed systems mass transfer is not allowed, but energy transfer is allowed. And this energy transfer in closed system, it can be done in two ways. One is heat energy, so in form of heat transfer, or in form of work. So in these two ways, energy can cross closed system boundary, and both of these are boundary phenomena. So if we have a system, for example, if we have a system here, and then if we define the system boundary like this by dotted line, so we define system boundary always by a dotted line, then energy can cross either by heat transfer or work transfer. And we will see that how this heat and work is conserved, or how we define an equation where total energy change is conserved in closed systems, and we call it as first law of thermodynamics. And before going into details of that, we need to discuss a very important experiment in history of thermodynamics, which is Joule's experiment. So we will discuss the details of this experiment. So what he did, he took a container like this, we filled it with water, then he arranged a paddle wheel system which is further attached to a weight. So this is a weight. Now once this weight will go down, this wheel will rotate, and we will see that when the wheel rotates, the temperature of this water will rise, and to study this temperature rise, he insulated. So Joule insulated the whole container, which means that there was no heat transfer here. And then he placed one thermocouple here, or thermometer, to measure the temperature rise. So thermometer to measure the temperature rise, and this thermometer was very sensitive. It was like 1/200 degree Fahrenheit. So the least count was this. So it was very sensitive thermometer. And by this, what he observed, that when the weight goes down, and because of this the paddle wheel rotates, which in turn increases the internal energy of water, which is reflected as a temperature rise. So what was the conclusion from this experiment? Until Joule performed this experiment, by that time everyone was believing in a theory that was known as calorie. So heat was considered as something which flows from one system to another, and that thing was called calorie. But when Joule performed this experiment, people now can say that work can be converted into heat, and Joule actually found a mechanical equivalent for heat, and he found that 1 joule of energy is equal to 4.186 calorie. So this was the conclusion from Joule's experiment. And by that, if we consider this as our system, if we consider this case again, so we can say for that system E2 minus E1, which is nothing but change in energy, can be equal to minus W adiabatic. And we are writing adiabatic because heat transfer was 0. So the whole system was insulated. And now why this negative sign? And this negative sign is because here work is done on the system. That's why this negative sign. So we can also write it like del E is equal to minus W AD for this thing, for Joule's experiment. Okay. Now we need to consider the energy accounting for closed systems. So for closed systems, we can say that del E, which is change in energy, is actually equal to the net energy transfer in and out across the system boundary of a closed system, which can be either in form of heat or in form of work. But in previous case, we just saw that this Q was 0. And to generalize the first law, we can write this. So in previous case, in case of Joule's experiment, this Q was 0. But to generalize it, we can say that del E is equal to Q minus W. This is the first law. So this is first law of thermodynamics. For closed systems. Now, also from our lecture 1, we know that this del E is nothing but combination of kinetic change in kinetic energy plus change in potential energy plus change in internal energy. And we will see later that for most of the cases, this kinetic energy or this potential energy, they are mostly negligible, and then we can say this first law of thermodynamics becomes like del U is equal to Q minus W. In most of the books, you will find this as first law of thermodynamics. Now we also need to discuss energy analysis for thermodynamic cycles. So, and by thermodynamic cycle, we mean, so first we need to define thermodynamic cycle. Thermodynamic cycle, and it can be easily understood from a diagram. So suppose we have property P1 here, P2 here, and we are going from state 1 to state 2 using a path this, which can be 1A2, and then we are returning to state 1. We are returning to state 1 using another path, which is B. So this whole thing can be, so the whole process, for example, 1A2B1, this can be considered as thermodynamic cycle. Thermodynamic cycle. And if we want to define, then we can say that it is a sequence of processes. So a sequence of processes that begins and ends at the same state. And we just saw that first law of thermodynamics is del E equal to Q minus W. And if you want to write it for thermodynamic cycle, then we can write it as del E cycle equal to Q cycle minus W cycle. And we know that for cyclic process, del E is 0 because it has come to the same state. So we can say from here that for cyclic process, Q cycle is equal to W cycle. Or we can also say that cyclic integral of heat is equal to cyclic integral of work. So this is first law of thermodynamics for cyclic processes. Now at this point I would like to mention some of the important points with respect to heat and work transfer. And before that, let us see some consequences of first law of thermodynamics. So let us discuss some of the consequences of first law of thermodynamics. Consequences of first law of thermodynamics. And we know this already, but we are going to see it in a more elaborated manner. So first thing is heat transfer is a path function. Now we are going to see how we can derive at such conclusion. Okay, so once again consider processes. So take this as property P1, P2, then define one state 1 here, state 2 here, and we can go from state 1 to 2 using different paths. So let us consider different paths. So from 1 to 2 we can go either by A, and then from 2 to 1 we can come either by path B, or we can also come by another path which can be C. So if you see here, we have two cycles. One is, suppose cycle 1 is 1A, 2B, 1, and then cycle 2 is 1A, 2C, 1. And we just saw that the cyclic integral of heat is equal to cyclic integral of work. So from here, we can write for cycle 1, what we can write for cycle 1 is del Q 1A 2 plus del Q 2B 1 is equal to del W 1A2 plus del W 2B1. So here I have done nothing, but I have just equated the total amount of heat going from 1 to 2, then 2 to 1. Again, total amount of work from 1 to 2, path A, and then coming back from choosing path B. Okay, and for cycle 2, we can write, again, this will be same. So del Q 1A2 plus del Q. Now we are coming from path C, so 2C1 is equal to del W 1A2 plus del W 2C1. And we can also note here that I am using this symbol del because the heat and work, they are not exact differentials, they are inexact differentials. And now we just need to subtract these two equations. So what we will get here, so these two will cancel out, then these two will cancel out, and what we are left with, del Q 2B1 minus del Q 2C1 is equal to del W 2V1 minus del W 2C1. And now we have already seen that work transfer is area under the curve. So if you see here, the work transfer when we are choosing path 2C1 is not equal to work transfer when we are going to choose path 2B1. So from our understanding that work transfer is area under the curve, we can say that this del W 2B1 is not equal to del W 2C1, which means that this further means that del W 2B1 minus del W 2C1 is not equal to 0, which further implies that del Q 2B1 minus del Q 2C1 is not equal to 0, which further means del Q 2B1 is not equal to del Q 2C1, and from here we can conclude that heat transfer is a path dependent. Heat transfer is path dependent. And similarly, we can also prove that work transfer is also path dependent. So if we see here, we can also say that work transfer is also path dependent. So similarly, we can prove that work transfer is also path dependent. And by this, we have come to certain conclusion of this whole thing. So regarding heat and work transfer, we can mention few of the properties which are like good to keep in mind. So for heat and work, we can say both are path functions, so they're dependent on path. We just saw that when we chose path B and C, they are different, so they are path function. Then they're not properties. So we cannot define work at a state 1 or heat at a state 1. they are always defined between like path functions. So we have to define that what is the work transfer when we are going from state 1 to 2, but we cannot define it at a particular state. Then both are inexact differentials, and that's why we represented it with some symbol del. And another thing is both are boundary phenomena. So we have not seen how they are like boundary phenomenon, and we will see it that how once we change the boundary, the whole concept changes. So let me take one example here. So suppose we have a gas in this box, and then we have some heater here which is powered by an electric motor. So this is our motor, and then the shaft here is connected by some weight. So once this weight will go down, the shaft will rotate, and this motor will behave like a generator. It will generate some current, and because of that there will be some heat transfer here. Okay, now we will appreciate that suppose if I am considering only the gas in this container as my system, then we can say that there is only heat transfer. So if only gas is considered as a system, then heat transfer is not equal to 0, but work transfer is 0. Now take another case. So another case where I am considering this whole thing in my system, so including this motor. So for the green box, if I am considering this as my system boundary, we can say that heat transfer is 0, but work transfer is not 0. And then we can also consider another case where everything goes inside the system. So for this case, suppose I am taking everything inside the system, even this mass which is falling. If I am considering everything inside the system, so if I am considering this as my system boundary, then for this case heat transfer is also 0, work transfer is also 0. So we just saw that considering the system boundary, we can change the whole concept. So I have considered the same system, but you have seen that somewhere it is like heat transfer is not equal to 0, but somewhere the heat transfer is 0, somewhere the work transfer is not equal to 0, and somewhere the work transfer is 0. So defining the system boundary also helps us identify what is the work transfer or energy transfer. And we will see other consequences of first law of thermodynamics in our next lecture. By then, thank you very much for attending the lectures, and I will see you in the next lecture. And if you have not yet subscribed to the channel, subscribe it so that whenever I am going to upload the next lecture, you don't miss it. Okay, so see you in the next lecture. Thank you.